We've used two fundamental approaches to circuit analysis, the time domain and the frequency domain. So far, we've kept those domains relatively separate, beyond using the time domain differential equations to derive the frequency domain algebraic equations. In this video, we'll compare how we characterize first-order circuits in both domains. This comparison will lead us to some valuable shortcuts for circuit analysis and some even more valuable ways to cross-check our results. First, let's do some review and minor extensions to our time domain analysis from first-order systems. The first case is the one we spent most of our time on. The governing differential equation is this. The output is y of t and the input can be written as u of t. In this case, we're assuming that the input function does not contain any derivative terms. The specific input for which we determined time domain responses was a step input, which was just a constant forcing function for times greater than 0. This was written as some constant value a times a unit step function u sub 0 of t. We determined the complete response as a function of time earlier, but for now we're just going to be concerned with the particular solution, which is the response as time goes to infinity. For a constant input, the derivative terms go to 0, so the solution is just a constant. The reason I'm only worried about the particular solution here is that we're going to compare this response to the sinusoidal steady state response in the frequency domain later. There's another important case that we didn't really address when we were determining first-order circuit step responses earlier. That's the case when the forcing function had a derivative term in it. I'll write the forcing function for this case as the derivative of some function u of t with respect to time. Now, if the function u of t is a step function, this is the form of the differential equation. Since the derivative of a constant is equal to 0, the particular solution in this case is just 0. Next, let's take a look at what these responses look like graphically. In the case where there are no derivative terms on the input, these are the shapes of the input and the output functions. The input's a step function that goes from 0 to a. The output is our typical step response shape. It starts at 0 and increases to its final value. An important parameter in system responses is called the DC gain. The DC gain is the multiplicative factor between the steady state output value and the input. If both functions start at 0, as these do, it's the ratio of the final value of the output to the final value of the input. More generally, it's the ratio between the change in the output value in the steady state to the change in the input function. The term DC stands for direct current. It's used as a shorthand to refer to constant values. The DC gain relates the steady state output response to the magnitude of a constant input change. For a system with derivatives on the input, the response to a step input will look like this. The response goes to 0 as time goes to infinity. The DC gain of this system is 0. We don't get a response as time goes to infinity for a constant input. Remember that a constant input is just a sinusoid with 0 frequency, and that the particular solution is just another name for the steady state response. That means that these results in the time domain need to correspond to the steady state sinusoidal response to an input with 0 frequency. We'll take a look at that next. Now let's look at the response of the same system to a steady state sinusoidal input. The input will be a number a times e to the j omega t, and the output is a phasor y times e to the j omega t. We don't need to use a phasor as the input because the phase angle of the input is not important in the frequency response. For the case of an input with no derivatives terms, this is the appropriate differential equation. If we substitute this input and output into this differential equation, we get this frequency response. For a constant input, the frequency is 0, and this is the response. For a system with derivative input terms, this is the governing differential equation, and the frequency response is this. Evaluating this at omega equals 0 tells us that the magnitude of the output is 0 at low frequencies. Both of these are consistent with what we got for our time domain analysis. Now let's take a look at the cutoff frequency in terms of the circuit's time domain behavior. This is what I'll call the standard form for the frequency response of a low-pass filter. The response is low at high frequencies and high at low frequencies. This form is the frequency domain version of the standard form of a first-order differential equation. In the standard form of the differential equation, the time constant appears explicitly in the differential equation coefficients. In the standard form of the frequency response, the cutoff frequency appears explicitly in the equation. I won't derive this from the governing differential equation, but I will show you that it's correct. The maximum response is at omega equals 0, and it's A over omega sub c. The response when omega is equal to omega sub c is this, which can be simplified to A over omega sub c times the square root of 2. This is just the maximum response, A over omega sub c, divided by root 2, which is the definition of omega sub c. So this form of the frequency response is correct. This is the standard form of a frequency response where the forcing function has a derivative term. The cutoff frequency also appears explicitly in this form of the response. Notice that this is a high-pass filter. The response at omega is equal to 0 is 0, and the response at high frequencies isn't. The maximum value of this frequency response is when omega goes to infinity, and the magnitude is just A. At omega equals omega sub c, the magnitude response is this, which simplifies to A over root 2, which is the definition of the cutoff frequency. Now let's compare these standard forms to the frequency responses we calculated in previous slides in terms of the circuit time constant. For the case with no input derivatives, which is a low-pass filter, this is the frequency response in terms of the time constant. Comparing these two indicates that the cutoff frequency is just 1 over the time constant. Likewise, for the case of a high-pass filter, which has derivatives on the input, comparing these forms also shows that the cutoff frequency and the time constant are inverses of one another. The important conclusion here is that the cutoff frequency and the time constants are inverses of one another. So if we know the time constant for a circuit, we automatically also have the cutoff frequency. Now let's use this information to develop an easy way to estimate the magnitude response shape of a circuit. This approach doesn't give a mathematical expression for the frequency response, but it does provide an easy way to determine most of the important design requirements: the DC gain, the high frequency gain, and the cutoff frequency. We've already seen that we can determine a circuit's response at low frequencies by replacing capacitors with open circuits, inductors with short circuits, and analyzing the resulting purely resistive circuit. The high frequency response can be determined by short-circuiting capacitors, open circuiting inductors, and analyzing the resulting circuit. The new trick from this video is that we can find the cutoff frequency directly from the time constant. The cutoff frequency is just the inverse of tau. This is helpful because for an RC circuit, the time constant is the capacitance times the equivalent Thevenin resistance seen by the capacitor. For an RL circuit, the time constant is just the inductance divided by the equivalent resistance seen by the inductor. We can easily calculate a time constant from these relationships and invert that to get the cutoff frequency. This works for any first-order circuit. However, it doesn't apply to higher-order systems. Next, let's do some examples of how to use these results in circuit analysis. In this example, we want to sketch a magnitude response for this RL circuit. The output is this voltage across the inductor, and the input is this current source. Any sketch should include the values for the low and high frequency gains and the cutoff frequency. We can determine all of those without calculating a frequency response. First, let's look at the low frequency gain. When omega is equal to 0, the inductor looks like a short circuit. By definition, there's no voltage difference across an inductor, so the magnitude response at 0 frequency is equal to 0. As omega goes to infinity, the inductor looks like an open circuit. There's no current through this open circuit, so this voltage is equal to this voltage. This voltage is going to be U times 5, so the magnitude response as omega goes to infinity is equal to 5. Now let's calculate a time constant and use that to determine the cutoff frequency. The time constant is L over Req for an RL circuit. The equivalent resistance is determined by killing the source. The current source becomes an open circuit, which means that these two 5 ohm resistors are in series and the equivalent resistance is equal to 10 ohms. So time constant, tau, is equal to 0.1 henries over 10 ohms, which is 1 over 100 seconds. Omega sub c is the inverse of that. So omega sub c is 100 radians per second. Now we have all the information we need for our sketch. The horizontal axis is frequency in radians per second. The vertical axis is magnitude of h of j omega. At 0 frequency, the magnitude response is 0. It increases to 5. So it probably looks something like that, with 5 being the maximum value. The corner frequency is where the magnitude response is its maximum value over root 2. So here at 5 over square root of 2, the frequency is 100 radians per second. And there's our sketch. In this example, I'll sketch the magnitude response of this RC circuit. The output is the voltage across the capacitor, and the input is this voltage source. We can determine the high, low, and cutoff frequencies using the shortcuts we learned earlier. First, let's look at omega equals 0. At low frequencies, the capacitor looks like an open circuit, and our voltage here is the same as the voltage across this 1 ohm resistor. This becomes a voltage divider, so y at J0 is half of u at J0, and the magnitude response at 0 frequency, magnitude of h of J0, is equal to 1/2. At high frequencies, the capacitor looks like a short circuit. The voltage across a short circuit is by definition 0, so the magnitude response at infinity is equal to 0. Now let's take a look at the corner frequency, which we can determine from the time constant. The time constant for an RC circuit is the equivalent resistance seen by the capacitor times the capacitance. We can find the equivalent resistance from this circuit. We short the voltage source. Now these two 1 ohm resistors are in parallel, and Req is equal to 1/2 of an ohm. Combining these and noting that the capacitance is 1 farad says that the time constant is 1/2 of a second. The cutoff frequency is the inverse of this, so omega sub c is 2 radians per second. Now we have everything we need to sketch the magnitude response. The horizontal axis is frequency in radians per second. The vertical axis is the magnitude of h of j omega. When omega is equal to 0, the magnitude response is 1/2, and it goes to 0 as frequency goes to infinity. So the shape is going to be something like this. At the cutoff frequency, the magnitude response is 1 over root 2 times the maximum value. So at the corner frequency, omega sub c, this is going to be 1 over 2 times the square root of 2. Omega sub c is 2 radians per second, and we're done. Being able to compare time and frequency domain analysis results is a valuable tool. It can allow us to take shortcuts by choosing the domain we use, and it can also allow us to check our results in one domain relative to the other.